Taking a look at the practice question set that we had to do for homework for today. It was practice question set number 3. Question number 1 has a graph representing force applied on a car during a period of time. We see a force versus time graph, and right away 3 words should come to our mind. Davin, what are those 3 words? Good. Area equals impulse. Let's scroll down and see what the question is. Oh, look, it's asking us what the area represents. This is the easiest question in the world, right? Once we've established that area equals impulse, the answer is B. We didn't even have to calculate anything there. Now, if you did calculate something before you read the question, it's not like you're going to get the wrong answer to the question just because you calculated something. It just would have been not necessary, that's all. Now, the next question is related to this, I believe. Yeah. Oh, it says the impulse experienced by the car from 2 to 5 seconds. We got to be careful with this one, right? From 2 to 5 seconds. What do you think the temptation of people to do is? What do you think that people will do to make a silly mistake? Yeah, like that would be so easy to calculate the area, the total area there, right? That's not what we want, though. We want the area just from 2 to 5 seconds, which is the area of a rectangle in the area of a triangle. The area of that rectangle is base times height. Oh, look at this. I should have circled this before, right? I missed that. 10 to the 2 newtons. Okay, we don't want to miss that when we're calculating the area here. Base is from 2 to 4 is 2. The height is 20 times 10 to the 2. See what I've done there? I could have just said 2,000, or I know the height on the axis is 20 times 10 to the 2. Doesn't matter if it's not technically scientific notation. That gives us 4,000, I think. Now the area of the second section, it's a triangle, so it's 1/2 base times height. 1/2 of the base, which is 1, times the height, which is once again 20 times 10 to the 2. And I think that gives me 1,000. We add those up, and we end up getting 5,000 Newton seconds. And sure enough, that answer is there. B, 5.0 times 10 to the 3 kilograms meters per second. Good. Next question. I think it was the last one. Yep. Group of students performs an experiment to explore non-uniformly accelerated motion in which the magnitude of the force increases as a function of time. Force is a function of time right away. Again, we're thinking those 3 words. Area equals impulse. Tells me the mass of the car is 0.50 kilograms. We've got a couple of axes here with units that are a little bit odd, 10 to the minus 1, 10 to the minus 1. Circle those or draw attention to them somehow so that we don't forget to include those when we find our area. Now the question actually asks us not to find the impulse, but to find the final velocity. The initial velocity is 0, so if we find the change, delta V, that's good enough, right? It's the same as VF, since VI is 0. Let's get the area first. Now, this one's a little bit tricky because it's on graph paper and not quite as clear on things. We're going to say area is equal to 1/2 base times height. And it looks like the base, it looks like it starts here at 0.5 and ends here at 8. So the base would be what? Yep. Yeah, I'm going to say 7.5 because that's what it is on the x-axis, and then I'm going to tack on the exponent there later, times 10 to the minus 1. Now, if you said 0.75, of course, that's exactly the same thing. Now, what's the height? Looks like the height goes to this line right here, which is 3.1234. Be careful. On the y-axis, we're going up by 0.1, 0.2, 0.3, 0.4, 0.5. On the x-axis, we're going over by 0.2, 0.4, 0.6, 0.8, right? Each vertical line is 0.2 as opposed to 0.1. So it didn't really matter so much on this quiz, but some other time, or on this practice question set, I should say, but some other time, when we need to establish that this line cuts through here, it wouldn't be 1.3, it would be 1.6. Okay, that's an easy mistake to make, right? Okay, so let's find this now. 1/2 of 7.5 times 10 to the minus 1 times 3.4. Just caught something. Just caught something because I had a red circle, right? What is it? Yeah, it's 3.4 times 10 to the minus 1. I would have missed that if I didn't have the red circle on the y-axis. And that's not just for dramatic effect. I would have like seriously missed that if I didn't have that red circle there. So 0.5 times 0.75 times 0.34 gives me a value of 0.1275. That's the impulse. Now we're going to set that equal to m times delta v. Rearrange to solve for delta v. Delta p is 0.1275 divided by the mass. What's the mass? 500.5 kilograms? I think it was. Yep. Divide that by 0.5, we get 0.255, or 2.55, 2.6 times 10 to the minus 1. The reason I put it in scientific notation is because that's the way they asked me to express it, right? Expressed in scientific notation. A decimal b times 10 to the negative c. A, B, C. You see what I'm doing there? A, B, C. My answer would be 261. And of course, we start on the left-hand side. If there's a blank, it's going to be the last box that's blank. All right? Now, sometimes they did this more in the past than now. You don't see this very often anymore, the way this way to express it, but every once in a while you still could. What if they ask you to express this as b times 10 to the negative w, which you do see from time to time, and they want the value of b? If that was the case, we'd express this to 2 digits as 2.6. Make sense? We would include the decimal place. It's not 3. We don't round it to 3. It's a 2-digit answer. B can be a 2 or 3 or 4 or 17-digit base, right? In this case, it's a 2-digit base. So usually this would be 261, and the way they ask you to express it here, it is 261, but they could ask you to express it so that the answer would be 2.6 as well. All right, let's take a look now at the check and reflect questions we had from our textbook for homework. And the questions that I had asked you to do were not 1 to 13, but rather 4, 5, 6, 11, and 12. Any issues there that we want to go over? 4, 5, 6, 11, and 12? First question to go over here, number 4, says, what's the effect on impulse if the time interval is doubled, if the force is reduced to 1/3 of its original magnitude? Someone in the last class brought up a really, really good point. He said, doesn't it depend upon whether the object is starting or stopping? Yes, it does. Because if the object is stopping, the impulse is predetermined, right? If the impulse is predetermined, then that means it doesn't matter what we do to the time interval. It's not going to affect the impulse. It's going to affect the force, but not the impulse. Does that make sense? We're going to have to assume in this question that the object is starting. That's what they meant. They should have said that, though, because if it wasn't, then things change. We're going to assume that it's starting. If it's starting, when we change the time interval, then we do affect the impulse. My original impulse is f times delta t. It is m times delta v, but it's not going to help me in this question. My new impulse, in question A that is equal to what? F times 2t, because I'm doubling the time interval. Let's pull that 2 out in front. I get 2 times f times t. And look at this. I don't know what the value of ft is, but I know that it's the old momentum, the original momentum. So I'm going to say my new momentum is simply equal to 2 times the original momentum. In other words, what happens when you double the time interval? You double the impulse. A lot of you probably just answered that question without even showing this, just logically knew that if you doubled the time interval, then you double the impulse. For question B, we're going to say my new momentum is 1/3 f times delta t, which, well, we know what f times t is. It's the original momentum, the original impulse, I should say. So it's going to be 1/3 of my original impulse there. Again, some of you probably did that without even doing any work, just logically thinking about it. Is that okay? Okay, number 5 was also requested there, so we'll go over that one. It says, even though your mass is much greater than that of a curling stone, it is dangerous to move for a curling stone to hit your feet. Why? Who's got an answer for me for that one? Yeah, Philip?
Your center of mass is a lot higher.
Okay, your center of mass is a lot higher. And if you apply a big force off center, then you get what's called a torque. Now, you don't need to know about torque in physics 30, but torque causes rotation. Okay, when I apply a force on this door, at the center of rotation, or near the center of rotation, not much happens, right? But when I apply the same force a distance away from the center of rotation, look what happens. It starts rotating. If you try to stop this curling rock with your foot and your center of mass is somewhere near your belly button, okay, then what happens? Well, you cause a torque and you end up falling over, right? You start rotating around your center of mass, you start rotating and you fall over. If you don't fall over, like, it might actually be good to fall over, because if you fall over, at least your foot is going to go away from the curling rock. If you keep your foot right there when the curling rock hits it, it's a 50-pound curling rock almost. They weigh almost 50 pounds, almost. And odds are, if you're just standing there, it's going to stop pretty quick. Predetermined impulse stops quick. Small time, what do you get? Big force. And all of a sudden you end up with a broken ankle. Good? How should you stop a curling rock? I mean, yeah, over a long time, right? If you're going to stop with your foot, first of all, make sure it's not moving very fast. And even then, make sure you kind of cradle it over a period of time. Okay? Usually you probably just let it run into other things and stop itself. And finally, number 6, using the concept of impulse, explain how a karate expert can break a board. The way we would break a board here would be a common misconception might be to set this up so that we would want to decrease the stopping time to increase the force, right? That seems kind of logical, right? Okay, if you hit it quick, you decrease the stopping time, increases the force, and therefore you're going to break the board easier, right? But the problem is, if you increase the force on the board, by Newton's third law, you're also, just one sec here, you're also going to increase the force on your hand. So maybe you break the board, but maybe you break the hand as well. So here's what happens. You're not actually trying to stop your hand, you're trying to start the board. So you're trying to impart as much impulse as you can to the board. So you do hit the board hard with a big force, but you also follow through. Somebody told me once the way you follow through in karate is that you look at the board's right here. You look at a point behind the board. So let's pretend that's the point, the calculator is the point behind the board. Now, I'm doing this to try to break the board, but I'm not aiming for the board, I'm aiming for the calculator, which allows me to follow through. What does that do? Well, I apply pretty big force, but what does following through do? Continues the force for a longer time. More force, more time, more impulse, more chance of breaking the board, right?